There was a question posted about my use of the words push and pop. I guess I've been using these words all along for several different things and just assuming that everyone knew what I was talking about. And that's apparently not the case. Push and pop are operations on a stack. So stack is some array. I'm using JavaScript because these are like common terms built into the JavaScript array object. So if we push the word apple and then we push banana and then we push cherry, then we have a stack, right? So it's pushing onto the end. Now, when I say stack pop, we don't say what you're popping. You say value equals stack pop. And so now value became cherry and the stack became apple banana. So we popped this off. The metaphor is this thing. The idea is that you've got a stack of lunch trays, right? And you push things onto them. And as you push them, you get a pop up, right? This is a different kind of pop. As you push things onto the stack, this pressure mounted tray is pushed downwards. And as you remove things, the spring or pneumatics or whatever it is that's inside of this thing pushes it back up. So as you take the item off, there's a kind of popping sound as the spring fires and the trays move upward. So that's where the words came from, as far as I know. That it's this metaphor of a machine like this. But you can also call it a LIFO. So for last in, first out, or first in, last out, FILO, right? And the idea is that they maintain state. So even in the middle of a program, you have functions that call other functions, and the computer will implement that as a stack. And so your computer has registers, like all the variables are stored in registers in the CPU. And when you call a function, all those registers are pushed onto a stack. So just in memory, there's an area that is called the stack, and it copies all the registers into that stack and moves the stack pointer up or down, depending on how it's implemented, so that it can remember like where everything was before it called that function. And then it goes into the function it's calling. It does all the stuff there. And then if that function calls a function, it pushes stuff onto the stack. And then when you get to the very bottom, you're done with the final function. There's a return call. And so you pop, you go back to the stack, you take all that data off, you put it back in the context, and then you return to the previous function. And now your context is restored, except the return value of the function is added to one of the registers, but everything else is restored. And then likewise, you keep popping off until you reach the top of the stack. So then you have two kinds of errors here. One is, I'm sure you've heard the phrase stack overflow due to the website. So a stack overflow is when you run out of memory. You keep pushing stuff onto the stack so much that you run out of memory. And so the stack has overflown. You've got too many trays on your thing. And then the opposite of that is an underflow, when you keep taking things off, and then you take the last item off the stack, and then you reach in and do it again. And now your stack pointer is screwed up and it's like looking into negative numbers or something like that. And so those are the two basic operations. Push and pop are for working with the stack, and then the two kinds of errors, underflows and overflows. So I use that phrase in three different places here. One, in just talking about my own mental state, pushing and popping things onto a mental stack, with the idea that at some point in the future, I'd like to actually show, like on the screen here, you can't see my cursor, but on the screen, like show, like, here's my goal. And then the next step would be like, okay, here's what I'm working on right now to achieve that goal. And then here's what I'm working on to achieve that goal, that sub goal, and so on. And that would be like somewhere on the screen, like in context, so that you could see, so that a viewer of an explanatory video could see exactly where you are in context. It's exactly like what in a debugger, you see a stack trace of where you are in the context of running a program. So I would like that to be a feature of our REPL for showing the viewer what it is you're doing, what it is that you're trying to accomplish. Like, not a computer stack trace, but a human stack trace. What are our goals? So I call that the goal stack. I guess actually on the REPL also. So here's my J parser stack over here. Let's say you type in my favorite line, PI10. So this is the sum of the first 10 primes. And so the way J parses it is right to left, and it uses a stack to do this. So it takes the input and it calls it a queue. All right, so now we have a string, and then I'm going to say, tokenize that for me, Jay. So it does that tokenization step. It sees these tokens, and now it's going to treat this list of tokens as a queue. So it's going to start here, and it's going to work its way through the queue from right to left. And the very first thing it's going to do is it's going to see the number 10. So 10 is a noun, and it could evaluate this, but it doesn't. It always waits until it has at least 3 items on the stack. And I'm going to go ahead and I'm going to show you something real quick so you know what I'm talking about. So it would be here. It's in the dictionary, parsing and execution. These are the rules of execution. And there's actually a trace verb that you can import to observe how this works. But so they're walking through an example here where it shows how to execute these parsing operations. And you're always looking at least 3 items. So these 3 items here. So once you've reached 4 items on the stack, which I'll get to in a second, it looks at those 4 items, and some of them might be empty, right? So if it's empty, then that's called edge. But it looks at the 4 things on the stack, and then it can use that to figure out which of the rules to apply to parse it. Okay. In our case, it's going to be very simple because we're always going to be using this first one, which is monad. So we're always going to have a noun and then verbs and then more verbs and then more verbs and then more verbs. So I guess this is actually this. So noun, verb. So these 2 items right here. Oh, actually, we'll do something different when we get here. So we have 10 on the stack. And so we don't evaluate that yet. We just push it onto the stack. And then we see I10. And so now we've got a verb and a noun. So that goes on the stack, I10. And then we see P, and that goes on the stack. And now we've got 3 things. And then we've got a backslash. Now we've got 4 things on the stack. So it goes through all these rules and figures out which one matches. And this slash character is a conjunction. Okay, so none of these match. And so we move on to the next one, which is this. And then I guess the next thing would be the edge, right? So the edge is here, which is the empty string over here. And so what eventually matches is a verb and an adverb and then any. So adverb fires. And what happens is that these 2 things get melded together and the adverb is applied to the verb. So now after that's done, instead of a plus followed by the insert, it has been melded together to form this new verb called sum. And so now we have a stack that has noun, verb, verb, verb. And that matches noun, verb, and then edge or AVM. So that matches this one. And monad is applied. And so what happens is this gets translated into 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we have the edge over here. So this is edge. We have a noun, a verb, and the edge. So this thing applies again. And this becomes, oh gosh, this becomes 2, 3, the primes, 2, 3, 5, 7, and so on. I'm not going to do them all. And then we sum them, and now we've got any here. So now it matches the first one. So any, this is empty. So this is empty. And it winds up matching this top one because the edge is on the left. So then we add those numbers together and we get 129. And so that's how the stack is used in the J parser. And so now I've finished that explanation. So I'm popping that off of my mental stack. And now I'm going back to why I'm talking about this. And that is that as you're working in the J REPL, I would love to be able to have, instead of just one line, oftentimes you have this big complicated thing. And obviously that's not J code, but you want to like take everything off to the left over here and push it. You just hide it temporarily so that you can work on the stuff on the right. So for example, like here, maybe if I want to edit this, I want to take it out of the string and I want to hide this for later. So what it would be nice to do is have a button that would push everything to the left of where you're typing onto a stack. And that would just be a second line up above. And then you could edit and evaluate the right-hand side and get that working the way you want. And then once it does what you want, then you can start pulling more tokens from the second line. So I can't show you that yet, but it might look like here in my imaginary REPL, I'm typing this line and I'm like, okay, well, you don't understand what this means yet. I haven't explained it yet. So I would like to break this into 2 lines. And so this becomes the token stack and this becomes the actual input. And so then I could run this and show you that I10 is equal to these numbers. And then I could say, okay, let's pop this off. And then I would show you P I10 and it would show you all the primes. And then I would pop this off and it would show you that. And so then you would see P I10. So that's how I'd like to use the stack in the user interface for the REPL, for J in particular. And for any kind of APL like language where you have this right to left parsing or just any kind of like stack parsing rather than like a context-free grammar. And of course, this gets even more complicated as you add in parentheses and compositions of verbs and all that kind of stuff. So I'm just showing you a very simple example right now. It could get very complicated. And so it can be nice to have a stack of these things so that you can move things around and swap things and whatnot. So I call that a token editor or syntax directed editor or whatever. So that and what am I working on at this particular moment in the context of the larger problem solving / narrative kind of thing. I want both of those things to be on the screen as stacks. All right. So then the other 2 places where I use the stack concept is one is in MJE. I currently have this idea of I have separate namespaces for each of the states for keys. And this is probably going to go away. But in J, you have this CO for classes and objects. So whenever you see copath, co-insert, all this, these have to do with namespaces, co-name. So I define co-push and co-pop. Really, if I made these both in the Z locale, then when I go into plain old J, I paste these in All right. So now you say co-name, you're in the base locale by default. So if I say co-push apple, then now I'm in the apple locale. And if I say co-push banana, I'm in the banana locale. And if I say co-path of banana, that's Z. But if I say co-path of apple, I'm expecting to see banana or base or something. Okay, if I say base anyway, it says apple. So if I say co-pop, now that says I was in the banana namespace. Now I'm in apple again. And if I say co-pop, I'm in base again. Yeah, I'm not sure why it's not. Oh, I guess because I don't do co-insert. Okay. I was imagining that the word co-insert was in the definition of co-push. But in any case, you can see there's a stack there. But the idea was, if you're using objects, you don't necessarily know that you're in the base locale. And in fact, maybe it's not a good idea to assume that. So rather than having an explicit name for where you're at, I use co-push and co-pop to just pop wherever you are onto a stack. And that way I don't have to say, when I'm done talking about the outliner keys, which is down here, I say co-pop. I don't have to say go back to base because it might not be base. I might not have started at base. This says go back to wherever you used to be. And then we can go into the editor keys and same thing for the REPL keys. So that was just like intuitive to me as like a way to make this independent of the base locale, the namespace. So that way you would be able to run this code at any namespace and it would have the same behavior. And then the other place where I'm using this push and pop concept is with terminals, or what I call the term stack. Basically, you got 4 different widgets on the screen right now, and each one of them is drawn by creating a buffer that is the same size as that widget, a memory buffer that holds the foreground color, the background color, and the characters of the screen. And so there is a stack going on where every one of the items on the stack has an interface that looks like a terminal. So the very topmost layer is just the VT namespace. If I break in the middle of this and I say stack of KVM, I believe, okay, it's empty. So if I say put s KVM hello, that's going to output the word hello. But now if I say a buff is, let's see, 30 connu of vid. So now I've got a video buffer and I push term buff. Is that going to work? Yeah. So now when I say put s KVM hello, you don't see it, because instead what it did is it wrote this to the buffer. So if I say render buff, render vid maybe, nope, KVM. Okay, the character buffer of this buff is, there you can see it, it's hello. I'm going to put it in a box. So you can see that it said hello. And then likewise, there's a foreground buffer and a background buffer. This says the foreground is all -7, meaning this gray color, and background buffer is that. And I have some word for rendering this thing. So names BT should be a name called render. Maybe I renamed it to blit. Is that why? Yeah. So if I say blit of that buffer, it's going to, I just wrote the buffer onto itself. So now I say top term, and now I say blit buffer, and you can see it wrote it to that screen. And if maybe we can have a buff2 is equal to, say, 55 connu, and then if we say fill buff2 with like x's, so now chb of buff2 should be x's, and if I say 1010, we're going to blit onto buff1, buff2, and then we can say maybe on the right hand side over here, so 50 and 2 blit buff. And now you can see that it's got both hello and the X. So we use these multiple terminals, and every time I want to draw a sub widget, I push a blank canvas onto this terminal stack and then draw that widget. That means it's every widget can just imagine that it lives in the upper left-hand corner of the screen, and it has a blank screen to work with. So it doesn't have to remember, oh, I have to check to see if there are any letters here and clear those out if they are. It just has a blank buffer to work with. It's a clear screen, and it simplifies the drawing logic. And because it's a stack, it allows you to compose things really quickly. It allows you to take whatever you've got on your current screen, set it aside, make a brand new screen, draw everything as if the cursor's in the upper left-hand corner. It's gray on black, and then it's an empty screen, and you draw your thing. And then when you're done with that, you go back into the previous terminal, and it's as complicated and filled in, and the cursor can be anywhere and all that stuff. And then you can blit the thing you just drew onto it somewhere. And then when you're done composing all that, then you move on to the next terminal. And finally, you get to the very end, and what you have is the ability, once the stack is empty, it will be able to just emit, and it doesn't matter to them whether they're drawing to a terminal or to one of these buffers. So that's my lesson on stacks, and then push and pop being the two most primitive operations on a stack. I have another repository called B4. It's actually under Sabrin B4. And this is a dialect of a language called Forth. And it's also a virtual machine. It's a bytecode that is itself a dialect of this language called Forth. And it's called B4. And my intent at some point in the future is to start talking about this on the show. And in fact, this will be a virtual machine on which I'll be able to run a lot of these tools. I actually want to port a subset of J to this virtual machine and use it to make my tool set like kind of portable between environments, so that I could run, like, say, the same JPrez or whatever inside of a game engine or inside of Smalltalk or something like that, like, just on top of Python, anything like that, in a web browser, anything like that. So that's what that is. And this actually is a stack-based machine. So in addition to push and pop, which I call put here, so we've got two stacks. We've got in a Forth, you have two stacks. You have a data stack and a return stack, one for your parameters and one for your control flow. I said earlier that you're pushing the current value of all your variables onto the stack when you're in like a function call setting. That isn't necessarily true. There are languages like Forth where you don't just have one stack, because the idea is you also push the instruction pointer, right? So you push all your data for your current function and you push the instruction pointer, but all onto one stack. And so that's the standard model. And like most languages, J and pretty much anything you can think of use that model, except for probably Forth. Even languages like Python and Java, where they compile down to a stack machine, generally tend to use a single stack where you push the arguments that you're working with and the instruction pointers to maintain your context. In Forth, those two things are separate. That you have the instruction pointer on one stack and you have the arguments on the other stack. And so what that means is you don't have to actually pass arguments to your functions. You just maintain the stack, because whatever's on the stack, you just jump to a function and then it uses that as the argument. It creates a language now where instead of having to write a function name and then parentheses and then all the arguments, you just call the function. And the function is just a single word. Those are called concatenative languages. And they have the same feel that you get with J and APL, where you have a pipeline like this, where you have 10. So in a Forth world, like this would probably be written differently. It would probably be written like 10 IP colon, and then I don't know how you would handle the adverb part. Probably it would be like this, maybe even. But so you would push 10 onto the stack and kind of do exactly what we did over here, but in reverse. So the way it handles the number is it puts the number on the stack. It sees this is a verb. So the way it understands that is it invokes that verb, passing it to stack, doing whatever, or it's a function. So it invokes that function doing whatever, and that function operates on the stack. So it takes the 10 off the stack and instead pushes the array 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 to the stack, and so on. So all of that was to say there's this language called Forth in which push and pop are like just like the way everything works. So just typing a number is push, and pop is like dropping that number. If you say like 5 push, 5 pushes the 5 onto the data stack, and then the push word says, okay, I've got whatever's on top of the stack. I'm going to take that 5 and I'm going to push it onto the return stack temporarily. And then you could say plus. So let's see, 1, 2, 5, push pop. That's your line of code. And so Forth would evaluate it like this. So 1 goes on the stack, 2 goes on the stack, 5 goes on the stack, push, takes this 5 and moves it to the return stack. So we've got a 5 over here. And then the plus takes these two numbers and it changes that to a 3. And then the pop takes the 5 off the return stack. So that is how you would evaluate this. And so in that case, in addition to push and pop, you have everything operating on the stack. So I say the push and pop are the primitive operations, but really there's like an infinite number of operations on stacks, including add the first two numbers, subtract the first two numbers, multiply the first two numbers. Almost all of them are like take 2 arguments. So anytime you have a function of n arguments, that can be a stack operation that takes the first n items on the stack. One of them is called swap, right? So you'd have 3, 5, that becomes 5, 3. And then there's another one for rotate when you have 1, 5, 3, and I think that becomes 3, 1, 5 or something, and so on. So if you look at the Java virtual machine or the Python's virtual machine, like they have this notion of bytecode and they're all stack operations. This B4 virtual machine is similar to that, with the intent that there will be some array operations in there. So data push or data put and a return put, and then top of stack, next on stack, swap, pop, get, set. These actually get stuff out of memory and put them on the stack. Anyway, that's a story for another day. But this is something I hope to cover in the future on the show. Once I get my presentation tools working, that will be how I will port those presentation tools to other platforms.